we started to
revise the probability. We have seen several examples and so on.
and we came to the point that we want now to talk about something which is called conditional probability. Now, up to now what we have done is this. I gave you a scenario, and based on that scenario you calculate some probability. For example, we had a die, we wanted to rule a die, and then we saw what the probability of that die is. Now this time we want to talk about calculating of a probability of an event if something else has happened. In other words, we want to put some condition for occurrence of our probability. So let's see how we define it and what are the rules on this type of probabilities. Probability of A given B. So we noted with this and we read it as probability of A given B is the probability of event A given that event B is occurred. So here we are talking about that one event is happening under the condition that another event has happened. As an example, we can stick with our dice. Rolling a dice has this sample space. What is the sample space of rolling a die? What is S? 1 to 6. Let's define event A to be one, two, 3. So what is the probability of A? We have 3 out of 6, so it's 3 over 6, so it's 1 over 2. Let's say B is occurrence of even numbers. Which means it is 2, 4, 6, right? And we know that the probability of B is also 1 over 2. Now, what we want to do is we want to calculate PA given B. In other words, we want to calculate what will be the probability of having event A if event B has occurred. Let's draw a Venn diagram. And let's specify what are the event A and B's. Now, the question is that we want to see what is the probability of happening A in case that B is happening, right? The probability of happening A in case B is happening. So, actually, B is dictating us what should be the new sample space. In other words, can we have some probability for occurring some number 1? No, because if 1, we have 1, B has not happened. Can we have any probability for 3? No, because B is not happening, and 5 is totally out of the question. So the only event that we have that if it happens, B is also has happened is 2. The only outcome that if it occurs B, the only outcome in A that if it occurs B has occurred as well is 2, right? Is 2. Event B dictates the new sample space. Why? Because we understand if anything out of B happens, is not considered because the probability is A given that B has occurred. So from these two we understand that the probability of A given B, we have one variable, one outcome, which is 2, out of how many? Out of 3. So the probability of A given B is equal to probability of B. Probability A given B is equal to probability is equal to 1/3. Now, one important thing is this. Notice that probability of A given B is less than the probability of B, which was 1/2, is less than the probability of A, which is also 1/2. In general, given that, can you see if I draw here? If we have this sample space S, and this is B and H, what is this? Sorry? It's intersection A, intersection B. Then we can have a formula of E A given B is equal to probability of intersection of A and B divided by probability of B. Obviously, or clearly, probability of A given B in general is not equal to probability of B given A. And in general, all these ones are less than equal. So let's have a few important rules, theorems, and they prove. First theorem that we want to plug in here is this. Probability of A given B plus the probability of A prime given B is equal to 1. Okay, think about it and see if you can prove it. In order to prove, we need to use the definition of conditional probability. Think about it for about a minute. Let's, by using definition, we have probability of A given B is probability of A intersected by B divided by PB plus the probability of A prime intersected by B divided by probability of B. They have common denominator, so I can write it as A intersected by B plus the probability of A prime intersected by B. Now, what can we say about A prime, and B? For 1 second, please look at here. This is B, and we have A also like this, which is intersecting. So this part is A, right? This part is A. What can we say about this part? This is A prime. Now, we had a very important name. What is this? We have another term. What A and A prime is doing on B? What is it called? It's called A and A prime are. What is the intersection of A and A prime? Empty, it's not 0. What is the union of A prime? It's B. So, we remember if two or series of things have no intersection and their union makes something, we call it A and A prime are partitions of B. In other words, I am dividing B into 2 or whatever number of parts. And if I put them all together, I will get B. Why this is important is because then from this formula, can you tell me that A intersected by B and A prime intersected by B, when they come together, they will make? They make? No, they make B. Don't use 1. Well, what happens is that, look, here I am in this red part. Here I am in the blue part. So if I add these two, I am in the B. So we get it that it's equal to, let's call it a star equation. So from the star equation, we get that we are equal to probability of B divided by probability of B, which is equal to 1. The above theorem is not true for B and B prime. In other words, we cannot say that PA given B plus PA given B prime is 1. It's not 1. You can come with an example which maybe for that specific example it is, but in general it is not. And apparently, probability of A given B prime is equal to probability of A intersected by B prime divided by probability of B prime, right? Which is equal to A intersected by B prime is actually probability of A minus probability of A intersected by B, because A minus A intersected by B is actually A intersected by B prime. And probability of B prime is 1 minus probability of B. If you add this with this definition, you see that we won't get A, we won't get 1. At the beginning of the class, I said that tomorrow the class is not in Noruse, it is in Chemicom in 10:20. It's only tomorrow, it's like that. So let's do an example. And the example is that the probability of a flight departing on time is probability of D, which is 0.83. So let's give the name. Probability of D means probability of depart. And if you want to depart on time, the probability is 0.83. The probability of a flight arriving on time is probability of A, and this is 0.82. 0.82. We are also told by the airport, let's say, that the probability of departuring on time and and arriving on time, which is the intersection of P of D, D intersected by A, is 0.78. This is the probability of departing and arriving on time. Part A. What is the probability of a flight arriving on time if we know it departed on time? And part B, what is the probability that a flight departed on time if we know it arrived on time? So here we have two events A and D. And we know the intersection of them. And basically what we want to know is that in the first part we want to know what is the probability of the flight arriving if the depart is on time. In other words, what is the probability of A given D? And in the part B, it said that what's the probability of flight departed on time, probability of departed on time, given that it arrives on time. Okay, let's say 1 minute. Please try to do it. So for part A, we want to calculate the probability of A given D, which is the probability of A intersected by D, divided by probability of D. We know that the probability of A intersected by D, or D intersected by D, they can interchange them, is 0.78. Probability of D is 0.83. And if you divide it, you will get 0.94. In other words, if we are departing on time, 94% we will also land and arrive on time. And in part B, we want to see the probability of D given A, which is the probability of D intersected by A, divided by probability of A. Again, the intersection is 0.78. Probability of A is 0.82. And if we divide it, we get the result to be 0.95. In other words, if we are arriving on time, it means that 94% we have also departed on time. Okay? Now, so we are talking about this given or conditional probability. Probability of this happen if something else has happened. Now, probability of, let's say, I wear this shirt if, let's say, thin air is departing on time. Okay? So this is a conditional probability. The probability of me wearing this shirt if thin air is departing on time. Now, question is this. If the thin air is departing on time, or if it delays, will it affect on me choosing this shirt? No. So there exist some sets of events that, although we describe them as a conditional probability, but we know that the occurrence of one has no relation, no dependency on the occurrence of the other one. Like I wear this shirt if the thin air is departing on time or not. Right? I can wear this and thin air can delay, or I can wear this and the thin air can be on time. So they are independent. So what we want to talk about is independent events. So I gave a very big exaggerated example. Now let's see, before I write the definition, another example. I have a die and I have a coin. And I toss a coin and I roll the dice, right? The probability of having head and the probability of having any number on the dice are independent, right? Because I can have head and the dice can be any number in there. Like if I have head, it doesn't make the dice to have, let's say, even numbers or odd numbers. So it means that they are independent from each other. So let's define the independent variable. Two variables, two events. A and B are independent if and only if probability of A given B is equal to she said 0. Any other opinion? The probability of, we said that blue and black are independent. So if I want to have blue, what should be the condition of black? We don't care because it happens even if this one doesn't happen, right? So the probability of blue given black is, does black affect on blue? No. So we don't care. So the probability of blue given anything is probability of blue itself. So it's probability of blue, whatever it is. So this is equal to the probability of A. Because A and B are independent. So this happen or not happen, it won't affect. The probability of, let's say, me wearing this is 1 over 10. So thin air delayed or won't delay, this is 1 over 10. So probability of this given thin air is the probability of this itself, right? Or probability of B given A, this time, it's probability of B because it doesn't depend on A. It's probability of B. Otherwise, A and B are dependent. So it's a very good way to test if two events are independent or not. So probability of A given B for, let's write in this for 4 independent events A and B the probability of A given B is equal to probability of A intersected by B divided by probability of B, which is equal to probability of A, right? So, for independent events, what we have, look, probability of A intersected by B is equal to probability of A multiplied by probability of B. If A and B are not impossible events, impossible events means that the probability is not zero. It's a number, but it's not zero. If probability of A and probability of B are not zero, which means that if probability of, if it means A and B are not impossible. Like if you are rolling a die, you cannot say a number which is divisible by 7. We don't have a number which is divisible by 7 between 1 to 6. So if it is not impossible, what can we say about relation between mutually exclusive and independency? So we do not have the impossible event. In other words, PA has a number, PB has a number, and so on. What can we say, Suman, about mutual exclusive and independency? Maybe we ask this question, that what was mutual exclusive, Thomas? They have no intersection. They have no intersection. If there is no intersection between them, it means that they are mutually exclusive. Now, what can we say if they are mutually exclusive? Like, if they are mutually exclusive, are they independent? Or if they are independent, are they mutually exclusive? Or if they are mutually exclusive, definitely they are not independent. Or if they are independent, definitely they are not mutually exclusive. Think about it. And one thing about teaching is that if there's a difficult question and I don't feel to answer it, I can always give it as a homework, right? But remember, mutual exclusive means there is no intersection between them. Independency means this. Write these two down and then try to see what can you conclude for events which are not impossible. In other words, they are possible. So in general, we said that the probability of A given B is equal to probability of A intersected by B divided by probability of B, right? And probability of B given A is probability of B intersected by A divided by probability of A, right? Now, from here, we can see that the probability of A intersected by B is equal to probability of A given by B multiplied by probability of B. And from here, we can see that the probability of B intersected by A is probability of B given A multiplied by probability of A. And because probability of A intersected by B is equal to probability of B intersected by A, can interchange A and B, then it means that the left sides of these two equations are the same, so it means the right side of them are also the same. Which means the probability of A given B is equal to probability of B given A multiplied by probability of A divided by probability of B.